Welcome back, everybody. Previously, we discussed the concept of potential difference. Today, we're going to apply that concept to see why charges move through a conductor.
Okay, so let's talk a little bit about what it takes to get electricity to do something useful for us. We talked in previous sessions about how a potential difference is useful for getting charges to move because it establishes a electric force. But that's not going to do us any good unless we can get those charges to actually do something useful, like, say, light a light bulb. Here I have a light bulb in a little light bulb holder, and I have two D cells connected together. Now the D cells provide a potential difference. There's a chemical reaction going on in there that causes a potential difference to be established between the different ends of the cells. And so I could just put the potential difference next to the light bulb and say, light up. Doesn't seem to do anything. Clearly, we have to have a way for the potential difference to be experienced by this light bulb. So we have a conductor, and I'm going to connect my conductor to one end of my D cells, and I'm going to connect the other end of my conductor to this part of my light bulb holder, and it still doesn't light up. Now, I think you have known since grade school, I'm sure, what it is we're missing here. We need to have something else in order for my light bulb to light up. Namely, we need to have the other wire over here, the other conductor, going from there back to the cells. And my light bulb lights up. So the question we have to address is, why is that needed? Why do we have to have a circuit? Once we understand the answer to that, we'll know a lot more about how electricity actually works.
So I have a question for you. Are there charges inside of a conductor? Even if the conductor is neutral, there are positive and negative charges inside the conductor. In a metallic conductor, the negative charges are free to move from atom to atom, while the positive charges remain fixed. Now, if there is an excess charge, it moves to the outer surface of the conductor. Again, we're going to depict positive charges as moving, but in reality, in metallic conductors, it's the negative charges that do the moving. They leave behind a positive surface charge when they move towards the interior of the conductor. As we saw previously, if you pile a bunch of excess charge in one location in a conductor, that means that there is a potential difference in the conductor, and the charges repelling each other will experience a net force. However, the charges will quickly rearrange themselves on a conductor so that there is no potential difference throughout the conductor. In a conductor in equilibrium, there is no net electric force on the charges inside the conductor. So let's see how this explains what we saw in the video. Let's say we have a battery that creates a potential difference. In essence, a chemical reaction causes one part of the battery to have an excess of positive charge and the other end to have an excess of negative charge. So what happens when we connect the wires to these positive and negative terminals of the battery? Initially, there is a potential difference in the wires. The excess charges repel each other. That means the charges experience a net force, and the charges flow through the wires. However, very quickly, charges spread out all along the surfaces of each conductor so that there is no longer any potential difference. This process takes only a fraction of a second. Even if we connect the light bulb to one of the wires, the process is essentially the same. The charges quickly rearrange themselves on the surfaces of the red wire and the wire in the light bulb, so there is no potential difference anymore. The charges no longer flow. However, If we connect both wires to the light bulb and the battery, something different happens. Now, the surface charge that is set up in the conductor changes from being very positive near the positive terminal of the battery to very negative at the negative terminal of the battery. Somewhere in the middle, the surface charge may be neutral. That is, no surface charge. Now, this varying surface charge means there is a potential difference throughout the circuit. A negative charge inside the conductor would be repelled from the higher concentrations of negative surface charge near the negative terminal and be attracted to higher concentrations of positive surface charge. It will move along inside the conductor. A steady flow of charges inside the conductor is set up. Such a flow of charges is called a current. These charges that are flowing are the charges inside the conductor. Keep in mind that even with this steady flow of charges, there is still no excess charge inside the conductor. Both positive ions and negative electrons are still present. It's just that now the negative charges have a net motion. So let's see this in a real-world example. In the following video, I will use a device called a voltmeter to measure potential differences.
Okay, let's look at the potential differences when we try to wire up our light bulb. Right now I have the white light bulb connected to the cells, but the other wire is not connected. So what we're going to do is we're going to measure the potential difference at various locations. I'll start out measure the potential difference from the negative side of my cells to the positive side. My assistant will tell us, my lab partner here is going to tell us what the potential is. What is it right now?
2.566.
2.566 volts. Okay, and then we'll measure it from the positive side of my cell to there on my light bulb holder. And what is it?
0.0.
0. Okay, and we'll measure from the one side of my light bulb holder to the other side of my light bulb holder.
0.
Still 0. And we could plug this in. Well, we could actually just measure it from, say, here all the way back to my battery.
0.
Still 0. But now, when we hook up the battery so that the current does flow, now let's measure the potential difference at each of the various points. So from the negative side of my batteries to the positive side, it is
Negative 2.55.
Oh, sorry, I have them backwards. Try it again.
2.55.
2.55. And then from here to there, the potential difference is
0.
essentially 0, okay. And then from there to there, so across my light bulb, it is
2.53.
okay. And then from across this side of my light bulb back to the battery, it is
0.
essentially 0.
For historical reasons, the direction of the current was defined as a direction that positive charges would flow. Now we know in metals only the electrons are actually free to move. So electrons moving to the left form a current moving to the right. The mathematical definition of current is as follows. Current is defined as the amount of charge that moves past a point in a circuit in a given amount of time. Now, since charge is measured in coulombs and time is generally measured in seconds, current is measured in a unit called an ampere, which is equal to 1 coulomb per second. So this discussion of charge motion begs the question, well, just exactly how fast are the charges moving? Well, the charges we're talking about are the outer valence electrons in a metal. They are not bound to any one atom. And they actually move from atom to atom at a pretty high speed, around 1,000,000 meters per second. Of course, the exact speed depends on the temperature. However, this is not the speed that we are concerned with. If there's no net electric force, that is to say, if there's no potential difference from one side of the conductor to the other, then the charges will move, yes, but they won't get anywhere. They will have no average velocity. Now, if there is a net force on the electrons, then they will experience a net motion in the direction of that force. The electrons will acquire some drift velocity, which is what we call the net velocity of the electrons. Now, drift velocities are actually very slow. By slow, I mean on the order of 10 to the minus 5 meters per second. That works out to be a few centimeters per hour. This is much slower than the average speed of the particles in between collisions. So if the electrons that are moving through the conductors are moving so slowly, why does a light come on almost instantaneously after you flip the switch? Well, we can apply what we know about surface charges now to understand that. The surface charges rearrange themselves very quickly, and so the charges start to flow very quickly. We don't have to wait for the charges that are in the switch to make it all the way up to the light bulb. There are various sources of potential difference that we can use in a circuit. Typically, we will use a battery. A battery converts chemical energy to electrical energy. The symbol for battery is this. You'll see the short line followed by a long line, another short line, and a long line. The short line indicates the negative side of the battery or cell, and the long line indicates a positive side. We will also might have a chance to see a generator in action. A generator converts mechanical energy to electrical energy. Current can be either alternating or direct. Alternating current, like ordinary household current, means that the direction of the current is changing back and forth. In the US, it changes back and forth 60 times per second, or 60 hertz. Direct current means that the current is going in one direction constantly. The current in a car's electrical system is usually direct current.